since I knew about the work of Tom Anderson for the last 7 years and met a lot of his students, but I never had a chance to meet him in person, even though I read probably over these years more of his papers than I read actually other literature. But Tom is a very well-recognized authority in internet measurement, and he has done one of the best work in the field in identifying internet on very fine granularities, properties of various portions of the internet. And what also impresses me is that he and his team are able to synthesize all the state-of-the-art that was achieved before. There are many teams that just do their own story and don't pay attention to what's going outside. But his team is not like that. Yeah, actually, yeah, you are looking at the overview, of course, of the best that Tom's team has done, but also at the best that measurement community have achieved over these years. Yeah, so.
Fair enough. Thank you very much for that kind introduction. So what I wanted to do today was talk a little bit about some work that we're doing. My group is more broadly interested beyond just network measurement on issues of how to build planetary scale or global scale distributed systems. And this effort that I'm going to describe here is really try to merge those two together. So can we take the output of the network measurement community, which has been making a lot of progress, has its own conference, does a lot of really great work, and actually bring it in some way, produce useful data that would be good for optimizing distributed systems. So that's the goal here, is to say, rather than necessarily think of coming up with great innovative new ideas, but rather can we actually produce data in a way that will be useful for distributed systems. And this is work with a cast of thousands. Different of these people have been doing different parts of this work. Arun is at UMass, and some of the, Yatin actually is now working for Google. But most of this has happened at the University of Washington. So actually what I'm going to talk about is 3 related problems. And they're related because of the following kind of common theme that goes throughout all of them. So the 3 problems are ones of, how do I know what physical location an IP address is in? And we're not going to answer that question, but we're going to say, well, what region is an IP address in? The second one is, can I predict what the properties of a path are without measuring them directly? So can I know what the likely behavior of a path will be before actually observing it? And that's useful just for a number of different applications. I'll talk about some of those. And then the final piece, and it's very, very recent, and that's why you can tell it's not been published yet, is on real-time black hole or brownout diagnosis. Can I know things about what's happening with respect to connectivity? The common idea behind all of these is, in addition to understanding topology, that is using all of the information sources that we have about the internet and integrating and synthesizing them together to be able to get better idea of what's going on, to be able to produce useful things for distributed systems. And all of this work is in work in progress. Even the parts that have been published, there are ones that we're still continuing to refine and improve. So one of the key observations about this, and I realize that being here at Google, this is going to seem obvious to you, but for the rest of the community isn't. Many people think that the internet's too large to measure, particularly measure in any kind of real-time sense and get useful online data about it. But clearly you do, just for web pages. But even if you just look at the topology of the network, it's actually pretty big if you take every link in every router and every end host. But if you actually aggregated it at a kind of coarser grained level, which is essentially at what level is there useful performance data, or what level is there useful data from a point of view of a distributed system, the internet is actually quite small. There are only roughly 100,000 POPs. That is, POPs are points of presence, that is essentially independently routable entities in different ISPs, and only about a couple 100,000 different prefixes that are independently routable. So you have a relatively small number of things that you have to actually go and measure, and that's what makes online measurement tractable. So for geolocation, the question that we wanted to ask was, could we come up with an automated way of doing identifying geographic locations of IP addresses. And you can think of the existing databases, commercial databases that I think Google uses some of them, that exist out there, and that are somewhat hand-tuned as well as some kind of mixture of automated and hand-tuned process. Our question, could we produce our goal really was one of saying, well, if we're going to start building the next generation of distributed services in the academic community, we should have an infrastructure that said, here, you give me an IP address, I'll tell you where it is roughly. So what our goal was to try to get it accurate to a major metropolitan area that allows you to do targeted advertising, and that it be a web service, and that the key thing, again, is going to be to leverage all possible information sources. I probably don't have to argue why you want to know where things are. I will only say that from our perspective, one of the reasons for us to get into it was actually a key piece of technology for us to be able to do some of the other work that I'm going to talk about. That is, understanding where things are ends up helping us kind of narrow down some of the possibilities that we might consider. For example, in doing alias resolution, if I'm observing different parts of a router, knowing that those different parts might possibly be in the same geographic area allows me to narrow my search down significantly. Okay, so here's the problem setting. I have a number of different vantage points. All of the work that we're going to talk about here leverages Planet Labs. So think of several hundred programmable vantage points around the world. In this case, this particular part of the talk is only going to focus on the US, just so we're in a defined region. We have a set of vantage points that I can make measurements between those vantage points. I can make measurements to endpoints. And those different kinds of measurements can either be pings, that is end-to-end measurements, just latency, round-trip times, or they can be trace routes. That is, I can understand what the sequence of topology is between them. That is, what sequence of steps, what routers they go through on the way. And I can also make measurements between landmarks. And then what I'm really interested in is locating the red dot. Right? That is some arbitrary point, some arbitrary prefix that is not a landmark, but one that I want to know where it is. There is a lot of related work, and I'm not going to talk about any of it. But what we're going to, I'm going to talk about one piece of that related work, which is called constraint-based geolocation, and explain why that doesn't work, and then talk about our approach, which is called topology-based geolocation. And again, that's the outline just for this first part of the talk. So if I'm trying to locate something in the middle here, you could think, okay, what I might do is I might ping it and integrate over all of the different circles that kind of round trip times from these various places. So if I ping it from various places, I can isolate where this red dot is going to be based on kind of the intersection of those. And that works really pretty well. I don't know where in this region it might be, but I do know that based on the round trip time, that it's going to be somewhere in there, and I might as well just pick the middle. And if I don't care, if I only need to know whether something is in Arkansas, then that actually works pretty well. The problem comes if that red dot is somewhere outside of the convex hull of the information sources that you're using. So if I'm in Florida and I don't happen to have a measurement node in Florida, which maybe I don't, then the world is really a lot worse off. So if you look at what's going to happen from my measurement point in Kansas, it's going to be pretty large, right? Half the US. Even the one in Houston is going to be, only narrowed down a little bit. And the one in Atlanta is going to basically say, okay, that's going to define my region. And if I take the center point of that region, well, actually, I'm going to find out that I'm going to think that everything that was in Florida is actually in Atlanta, which isn't really what I wanted. So the question is going to be, how do I get better reliability, given I have all this information, but I might not have vantage points in all the right places that I want. So if I evaluate this kind of constraint-based approach, this is, again, published research in the measurement community, what you'll see is systematically that the error goes up as a kind of linear function with how far I am from a vantage point. So the closer I am, the better I can get the estimate. The farther away I am, the worse off I am. And so if I'm close, then if you're close, then okay, that says you're within, you know that you're close to the vantage point, therefore you've got a fairly tight bound. If you're farther away, if you're far away from a vantage point, then all bets are off. So can we do better? Can we do well for the case where you're not anywhere close to a vantage point? And the real problem here is that these distance points are unconstrained. They could be anywhere. And just based on the kind of round trip time, you're not going to know any of it. So the hard part here is going to be to use, or the two parts of this equation are going to be to use the topology of the network to be able to constrain the locations of IP addresses, and then essentially to run a constraint solver. That's the easy part, is to run the constraint solver on that. So here's a couple examples of ones where you can see the kind of behavior of the system. For example, if I have a path or various paths between my systems, well, any of those round trips can take wherever. Z, if they're going to T, may actually take some circuitous route. And if I have a circuitous route, again, I'm going to have a much larger window in which to place something. If I happen to know, as a consequence, I kind of guess in this example, I'm not going to get a very close relationship to T. But if I can place R, that is, some router that all of these nodes go through, then I can limit the bandwidth significantly. In this case, the intersection of the router may well actually be fairly well placed, and then the placement of the node beyond that is just then a straightforward region around that router, even if I don't know anything more than just where that router is. And you can see how that's going to be a much narrower bound on it than other ones. We're going to add some techniques to this over time, but that's the basic idea. Okay, one of the key things about this, you might think that I could do this just, the simple case that I just did, which is solve a given constraint by itself and then go on to move to a different constraint. And what I'm going to argue here is that I need to be able to solve all the constraints simultaneously. That is, I have to actually treat it like it's a constraint solver rather than an iterative process. So in this case, I have X that knows where R is, and Z that if it's trying to place, I guess that's trying to place R, right? I'm not actually going to be able to place R very well, right? The region that this R is going to be in is now, fairly large, but maybe it's okay. And if I do the same thing for S, I think that's what we're doing here. I can again place S. And now if I add to that the notion that I can bound the relationship between S and R, because I can do per hop information, then I can end up with a bound. If I add that to the bounds that I had before, then I end up with some fairly narrow positioning for R. That is, the ability to use the information that Z and Y were close to S, and that S was close to R, added to the information that W is close to R and X is close to R, allows me to get a fairly narrow point on the information about R. So the final point that I was going to make about this, I think this is the final point, again, these aren't my slides, is that it's very important to be able to cluster information about different routers together. And this is going to be this common theme, that you want to be operating at the right granularity. So in this case, if I don't know that S and R are close together to each other, for example, that they're both interfaces on the same router, or if I can't know that they're part of the same POP, then my information that I have about placing S and placing R are going to be aren't going to give me as much useful information with respect to T. In this case, if I only can see in my traces X going to T through R and Y going to T through S, then I'm really not going to have any great understanding of where the combination is. So if you kind of look at it from this perspective, the outcome of this is going to be a fairly large region, because I have to say that it's where S can move and where R can move separately. Whereas if I can somehow say that both of these are the same router or connected together, then the region is much, much smaller. OK, so now, I actually forget what this says. Another issue that you can have is that you can get estimate hop lengths as well. So the basic model of the approach is one where you have known locations of landmarks. You're going to have RTTs from these landmarks to constrain feasible locations for all of the intermediate hops between you and the router and the targets. And then you're going to then run a constraint solving problem on the whole thing in order to yield the result. And what you can find is that this is actually remarkably effective. Right? That is, being able to over-constrain the problem, knowing the topology of the network allows you to be able to solve the problem for a much greater degree, which is, so if this was our CDF, so that's a cumulative distribution function of essentially any point on here says that there's a 20% likelihood that I have found with the old scheme a 20% of the route of the positions that I find in the old scheme are within 250 kilometers, and some portion. And remember that all of these points, by the way, are within the continental U.S. So, actually, it's remarkable that there are so many that are so large, right? 1,000 kilometers is larger than Texas. So you have some large section of them. The median number is about 800 or so kilometers, not actually very, very specific. Whereas if you have this kind of topology-based constraint, then you can get a median error that's much tighter and does better on the kind of worst cases. Now, the second part of this work was to try to, okay, what other pieces of information can we have that'll help us locate this information? And there are lots of different information sources, and we're only going to use a few of them here, but it's an indication of how you might be able to integrate topology information with other information sources. And in this case, you could use some available database that you could go buy. There are other pieces of information. For example, DNS locations in many routers have DNS information and their name information that encodes some information about the location of the router. It's often wrong. That is, sometimes you'll see a router with a name, that's actually physically located in New York City that happens to be, happens to have a name that had been moved there from some router that had been in Topeka or something like that. So this information that you can get out of DNS is not always accurate. And one of the things that we had done in previous uses of geolocation information was to just manually go in and fix the information that we could get rid of. So the question here was, could we come up with safe ways of using the information that would allow us to use it without with an automated technique? So in this case, for example, I might have a hint that a particular router is in Boston, say, because it's got a name that uses BOS in its name, and then another one that has LA in its LA in its name, and then I have some information that I have. Oh, and say another one that I think might be in Detroit, and I have a landmark in San Francisco. Clearly, San Francisco is a long way from all of these, but I can potentially know information about clusters of things that would help me. For example, if I know that these things are hinted to be in Chicago, well, and these things are all a cluster, then I could say that that also is a hint for a cluster for Chicago, and that therefore, if it's the case that that these are all really close together because of their their latencies, and therefore this has to be constrained to be close to Chicago, then this probably can't be a hint for Boston, right? So that hint is probably wrong. And essentially, you do some kind of weighting mechanism in order to do this constraint solving simultaneously. Similarly, once you placed one of them, then you can verify that some other hint that you have is inconsistent with the other hints that you have. For example, clearly Los Angeles is not 5 milliseconds away from Chicago, and so we'll have to drop that hint off and not use it. And then speed of light times round trip time limits the path length. And then that gives you some bound for saying that the rest of the world is then consistent with that. Okay, so here's an example of where this really pays out. Basically, if you're traipsing down, and this is why we started introducing this information, if you're traipsing down some part of the internet topology and you don't have any kind of cross links between things, but rather it just looks like a part of a tree limb that just by itself. In this case, the only way that you can get from Planet Lab to Alabama A&M is through this router in Atlanta, and it's just how all the packets are routed through Alabama A&M is coming at it from this router in Atlanta. It's in general a bunch of the internet has this property, particularly in the third world. Then the kinds of solutions that I talked about originally with respect to placing routers really wouldn't tell you much, right? Because you're just seeing this long chain and say, oh, okay, this location that happens to be in northern Alabama really could be anywhere within a 5-state region. So are there things that you can use with respect to hints? And one of them would be that I have a hint that this is in Birmingham because of the label of the router, which would be BRHM. that says, oh, okay, maybe that's probably Birmingham, right? I don't know for sure, but it's consistent. And then I can, if I believe that hint, then I could, or I verify that hint is at least consistent with all the other data, then I can then place Alabama A&M at least within Alabama. And then if I have other information, for example, the location of the University of Alabama Huntsville, and then I know that the IP address for Alabama Huntsville is, in fact, a certain location because I know where it is on the map, then I can use that information similarly to be able to bound the router that's upstream from Huntsville, and then as a consequence of that, where that Alabama A&M has to be somewhere in northern Alabama. That's the idea anyway. And if you take what is essentially the worst possible case for what we do, which is university data sets, and the problem with universities is they tend to only be routed down these long chains, then you actually do much, much better using these topology-based information with passive hints. And if you can think of doing war driving or adding additional information that seems quite plausible, you could do a lot better than this. And if you can kind of consider this compared to where we started, this kind of median error is only about is within a metropolitan region. It's only about 50 to 60 kilometers. And I should say this is all for locations that are far away from, we've restricted this to only those locations that are far away from a landmark. So if you're close to a landmark, then of course you're going to get a fairly close tie-in. Right? Essentially, it's how do I simulate the behavior of a landmark if I don't have one. Okay, so this kind of summary here is that these purely delay-based techniques, those purely ping-based techniques without an understanding of the underlying structure of the network don't help you too much. Understanding the topology of the network at the right granularity helps you a lot. That is, you have to actually understand which routers go with each other, because you can't actually measure every interface to every router and place them well unless you actually understand the constraints between some of those routers with each other. And then if you can add hints into the system, then you can actually end up improving the case where the network structure is insufficient for bounding. Okay, so I'm going to move on to another a case study that's similar. That's, again, our goal here was to be able to produce data that's useful for distributed systems. And here what we're going to do is to try to predict path performance. And there's a couple papers that you can read up on this. And what I mean by path performance, I mean all different kinds of path behavior. And again, I'm predicting it rather than measuring it directly. I'm using other measurements of the system to be able to tell what's going on. And here's the motivating example here is BitTorrent. If you look at how BitTorrent works today, I go to a tracker. The tracker returns, so in order to go find a BitTorrent swarm, I go to a place that's going to tell me all of the other people who are current, or some subset of the people who are currently downloading the file that I'm downloading from BitTorrent. So the client tracks this, contacts this thing called a tracker, and that then provides a list of peers for me to go get. And that sounds great. And today, the default behavior is to return a random number of these peers, so random selection. They could be anywhere in the world. But clearly, what I want in terms of what I'm bringing back from the tracker is some more directed set. Right? I'd like to have ones that are close to me in some meaningful way. So out of the total number of people who are downloading a swarm, I'd like to somehow know that these ones here are likely to give me a high bandwidth connection, or likely to be low latency, and those other ones over there might be random. So you don't want to only base the results, the returns from the tracker, only on locality. Again, what that would do would be to tend to create little clumps of clusters and not and essentially disconnected pieces. You have the swarm for North America and the swarm for Europe. So you want some amount of randomness to be thrown in as well. But you do want to favor the notion that I might be able to download from people who are local. Right? If I know, for example, that somebody else at the University of Washington has already downloaded something that I'm interested in, already downloaded the Linux distribution, it makes no sense at all for me to go off to MIT to get that distribution rather than going there. That's the idea. That is, how can we build better swarming systems using this? Now, what that requires me to do is, from the tracker's perspective, predict between any 2 points in the network what the good performance is, right? And I have to do it without any measurement. I have no active measurement between those 2 points, right? I'm just trying to return something to somebody, say, here's the ones that you want to use. There are existing techniques that will give me latency predictions. They're essentially treat the internet as a black box, and really cool systems. I mean, just you really amazingly weird that they work at all. So just to give you an example of what GNP does, it embeds the internet in a hyperdimensional cube that is, n-dimensional, 7-dimensional. It's like, how did that work? And then tries to basically point fit, closest fit, the measurements that it's making between the various landmarks and endposts to be able to locate endpoints and landmarks within this n-dimensional scheme. And then from that, then takes the Euclidean distance from it. This has no rational basis for how internet routing works, but it's remarkably good because basically curve fitting works really well in a lot of different cases. The real problem with it isn't that it doesn't work. It doesn't work great, but it works pretty well. And actually, you can find Azurius actually uses one of these versions, which is called Vivaldi, which is a little bit simpler than full GMP, but basically based on the same idea. Actually, Azurius, which is the most popular BitTorrent client, uses it in order to be able to judge who they should be connecting to, or who they should favor for giving BitTorrent communication with, because you want to go to people who are close to you because they'll likely have better bandwidth. The real problem with it is that it's not extensible to other bandwidth. It only gives you latency predictions. It doesn't give you bandwidth predictions. Yeah.
Has anyone looked at the real correlation between bandwidth and latency? I would expect for all sharing networks that bandwidth be essentially a function of link bandwidth. So essentially of the number of clients that are talking to a given node.
Yeah. So.
Uplink to the internet is a megabit, then it doesn't matter where you are. When you separate that megabit, your performance is going to.
Yeah. So let me see if I can translate what you'd say. Clearly, latency is unrelated to access link bandwidth, except if. In general, depending on where I am sampling you, I could be very close to you or I could be very far away, and I don't know what your access link bandwidth is as a consequence of that. So one thing that is true is that, and it's a kind of separate thing that we've been looking at is there is a wide diversity of different bandwidths that different peers will have, and as you might imagine, a large number of people have got DSL or cable modems or whatever, and then some number of people who have just very, very high bandwidths. And so in order to actually do really well within a BitTorrent system, you would like to connect the people who have very high bandwidths. In general, particularly if you're high bandwidth yourself, you really want to go find the people who are high bandwidth. And that's almost independent of latency in that sense if you're trying to do fast downloads, particularly if you can amortize it over a longer period of time. The people who have a lot of bandwidth actually add a lot into the system. In this case, we're actually asking this of the tracker. That is, we're saying, okay, if the tracker is going to try to organize who's talking to whom, and that's really the tracker's goal, how can it do that strategically in order to improve the performance of the system? And in general, even if I'm just talking between DSL modem or DSL customers, I want to connect the people who are close together just in latency, because they'll be able to transfer faster and get better TCP throughput than ones who are talking farther away. Okay, so the structural approach here is to use measurements of the internet structure to predict the end. So the two parts of this I should point out. The structural approach is one that's going to use the structure of the internet to be able to make these predictions. And then what we're going to do is to use measurements of the internet structure to predict the route that the packets are going to take between these two points, A to B, and then measure and compose the properties of those links in order to on that predicted route in order to get the performance. And I'll show you this in a second. And this is the work here is called iPlane, and the idea is going to be that it's going to predict path properties on the internet, and then predict multiple metrics, and then use it on distributed services. So it's going to have four parts to this. One is that I have to be able to know what the internet's going to look like. A lot of that same structure of what I had in the previous part of the talk. I have to be able to predict routing. That is, if I don't know what path somebody's going to take between 2 points, it's going to actually be pretty difficult for me to understand what their bandwidth is going to be, right? Or what their latency is going to be, or what their loss rate is going to be. It just, if I don't know where they're going, then it's going to be very difficult. So I have to be able to predict the actual routing between these two endpoints. Despite the fact that I have no measurements, I have no ability to do trace routes between them. And then finally, I have to be able to measure these properties of measure the properties of the links in the core, and then And then finally, one of the big challenges here is I have to be able to measure the actual edge and access link bandwidth. That is, I also want to know what the bandwidth is at the edge of the network. So I'm going to use a bunch of information that we have in order to build the structured atlas of the internet. Again, I'm going to use Planet Lab. Also, there are a set of public traceroute servers that ISPs host around the world. And so we're going to use that information to build an atlas of routes. And then what we're going to do is from these various traceroute servers plus Planet Lab, do trace routes to various prefixes. Again, we're going to try to aggregate at that level. Cluster these interfaces into POPs, and then repeat this, repeat and lather and rinse. OK, so that's the structured atlas is really one of, OK, measure from a lot of different vantage points to pretty much every prefix in the world. And you think, OK, that's too many addresses to go do. But if you're aggregating at the prefix level, there's only a couple 100,000 of those. And then try to cluster those into POPs. So OK, there's only 100,000 of those. And then measure the inner POP links. OK, there's only a few 100,000 of those. So it's actually, from a measurement perspective, actually a relatively tractable problem. OK, so I can build this structured atlas. And then the next problem that I have is how do I do path prediction? And here, again, we're going to steal, sorry for the washout here, but we're going to steal some ideas from the rest of the internet measurement community. So I have a set of different measurements that I might have made. And apologize for the washouts, but figure these things are just various cities that I have. So Seattle up there might be a vantage point. I have another vantage point in Rio. I can measure from Seattle, and another one in Chicago. I can measure from Seattle to all prefixes. So I have measurements from Seattle to Portland. I have measurements from Seattle to Paris. I have measurements from Chicago to Portland, Chicago to Paris. I have ones from Rio to Paris, Rio to Portland, whatever. So I have this whole mass set of things, and they all intersect and combine in different ways. And you can see that if this pink one is the real path between Seattle and Portland, somewhere in my database, I probably have something that closely approximates the actual path that's being taken by this. I may not know what that path is, and I may not know where to find it in the database, but somewhere in there I probably have something that's pretty close. And so the goal here is really to try to identify this by trying to find places in my database where I can find intersections of paths so that I can use path segments, say this one from Chicago into my source, and this one from Seattle off to my destination, that they happen to go through the same router or through the same POP, and thereby give me a prediction. Now, I have to also be able to exclude ones where there might be intersections that are farther away or less likely than the other ones. And that's going to be a key problem for making the system work. So I have to use the ones that seem more likely to be useful. And the way that we're going to do that, and again, I'm going to point you to the paper for details, is to use the ones that internet routing will more likely use. So we understand a lot about how internet routing work, what the policies are that ISPs use, and then essentially model those into the algorithms in order to say, OK, this intersection is more likely to be one that if the ISPs are acting rationally, they're likely to use. So for example, early exit or shortest AS path, those are the ones that you would like to use for these intersection points versus things that are farther away. OK. The second point that I would make about this is that it's very important to be clustering interfaces. So for example, in this case, it might well be that the vantage point going to Paris, or the destination, actually goes through a router that's not actually the same router as the one going in the other direction. And that's actually, it's very common for it not to be the same interface, but it actually might just be a different router in the same POP or a different router in the same neighborhood. And so what you'd like to be able to do is to actually cluster them together, and it'll actually do you a lot of good with respect to the accuracy of your system to be able to cluster information that's related to each other. But it means that you don't have to have you don't have to find a measurement that goes through that router. Rather, you can find one that goes through any of those two routers. And so this ability to cluster into POPs actually ends up being essential to the success of the system. And then we're going to do this using a lot of the techniques that I talked about earlier, which is essentially discover locations based on names and inferred locations, and then run a set of algorithms that are standard in the literature, of which we did some a few years ago, to identify routers that are close together, and then essentially look for routers that are very close in latency and also very close in hop count from the other routers in the same cluster. So here's an example. Actually, you can I think Harsha, is this online? You can try it out. I'll give you a web page at the end. This is Harsha gave this talk at IMC, which was in Rio, and did a traceroute as an example. This is the actual path that you take from Rio to, what was it, an embassy in what? No, that's not Belgium. You're going to, no, it's Romania, right? Romania, okay, yeah. I was thinking, no, that's not Belgium. Your European geography really needs some help here. Okay, so so from Rio to a location in Romania, and then here's what the predicted path is. It's not exactly the same, but in terms of overall latency, it's pretty close, right? That is, what this does is to use some path from Rio, basically from a vantage point in Rio to where his hotel was. Sorry, from a vantage point in the U.S. to where the hotel was. Ended up looking like it was likely to be the one that was useful, and then from that one over to the other side. And it's not going to be exact, but it's going to be usually gives pretty close behavior. One of the key things here is that how often does this path prediction work, and which is how often is it the case that the AS path is what you would expect. Given that I have no other information about it, I don't have any measurements from the source. I don't have any measurements from the destination. I just have, BGP reachability information and other traceroute information. How often am I able to actually predict the path that path from using this algorithm, where we actually know what the path is? In some cases, we can know because we can do direct measurements. And in that case, then you're getting the actual path, the exact path. About 70% of the time, and then some increasing amounts of some portions of the path, some of the rest of the time. So so in many cases, you're actually able to predict the AS path, which I'll show you in a second, ends up being essential. So okay, given that I can predict the path, then it becomes actually a pretty straightforward thing to go predict end-to-end properties. I have to go and measure. Along every inner pop link in my network, of which there are only 500,000 or so. So that's pretty easy, and then combine them in some rational way. So in this case, take products of loss rates, which isn't literally valid, but is close enough. Sums of link latencies and minimums of bandwidths. And then the one final point, I should say, I then have to measure links in the core in order to be able to do that. That's actually pretty straightforward. And then the final point is, how do I actually estimate edge access link bandwidths? And this is something that if I was at Google, it'd be pretty easy because you get a bunch of bandwidth, you get a bunch of customers at each of these prefixes actually contacting you. In our case, because we're at a university and we want to be able to publish our data, we have to use data. We have to use data that's available. So what we did was, okay, there's this really popular system out there that's got 6 million people who are all open to having a torrent that's going to tell them, here, connect to somebody who's now joining a swarm. So we passively join a bunch of BitTorrent swarms, and then essentially look at the packet pair distances between pairs of packets that are returned from downloads, and that gives us an estimate of the upload bandwidth. It doesn't actually tell us what the download bandwidth is, but it gives us an estimate of the upload bandwidth from different sources. And because it's just passive monitoring, it actually doesn't raise any alarms. We actually don't download well, in some cases we do download content, but in this particular example, we're not downloading any content at all from the actual BitTorrent peers. We're just connecting to them, downloading a block or two, and then say, oh, okay, that's good enough for us to get our measurement, and then we go on from there. Yeah.
Have you link bandwidths from the measured bandwidth?
Oh, so
I would expect that to be linearly varying with the number of clients that node has. Is that known?
So no, what we're doing is we're trying to estimate the, in this case, the access link bandwidth. So just the little part that the end host is doing, and we're going to do that by looking at the distance between packets that are being retrieved.
You're effectively measuring the packets that you get from the node.
Right.
So you're effectively measuring a fraction of the link bandwidth, which is.
So if we were measuring the if we were measuring the end-to-end behavior of the connection, then what you said would be true. We would be measuring the effective bandwidth would be some fraction of the total access link bandwidth. However, if you look at the inner packet distance, or the minimum inner packet distance that you observe between packets, TCP congestion control will do this thing called ACK clocking, which in general will cause it to send back-to-back packets on a regular basis. Those back-to-back packets will tend to traverse through the network together. That is, they will tend not to be interspersed with other traffic that's going to other connections. As a consequence, it gives you a relatively clean read as to what the actual access link bandwidth is.
So you're saying that TCP stacks on the host will bunch together packets belonging to the same connection?
Yes. And then just the natural behavior it does because of the way it does ACK clocking. So whenever I increase my congestion window sufficiently to be able to send another packet, I will send those two packets back to back. I'll send them as fast as I can. And if the access link bandwidth is in fact the limiting factor, then those will actually go out together, right? And now we have to do some kind of signal, everything. So one of the things that's very clear about this is that everything that we do has noise in it. I mean, everything that we do is not perfect. It's not a clean signal. So you have to be able, whether it's the label on the DNS name for the router, or in this case, you're having to do signal processing or some kind of ability to throw out noisy data. And that's really one of the essential pieces of this that makes it a lot harder than it looks, just from a kind of logical side. But you can actually, it's a well-known technique within the network measurement community to be able to use just a regular TCP transfer, one-way TCP transfer, to be able to estimate the bottleneck bandwidth that went through. And it's because of the dynamics, because TCP is not doing pacing of its packets, it's not evenly spacing its packets, it's actually bursting them, that allows you to be able to do that. Yeah, sorry, did you have? Okay.
Result in the same.
That delayed acknowledgements, yes. It turns out that it's easier to do it on the forward path because you've got actual large packets, and it's a little bit more difficult to do. Yeah, so it's possible that you could also play tricks with TCP to be able to trigger packets coming back, and that would be another way to do it. But we just passively listen to what people are going to send us. We're not actually doing anything other than, connect to you. You have something, let's go listen to it. So here's an example of the kind of data that you can get out of this, which is how often is it the case, because we've got a very large number, actually, we've got a very large number of hosts. We haven't connected everybody who does BitTorrent, but it's pretty easy to go connect to a lot of people. How often is it the case that different prefixes with different addresses within the same prefix give you the same measured data? And the answer to that is this cumulative distribution function, which is about 2/3 of the time you will see this data that's coming back from this signal as being within about 20% of each other, which is to say that you're getting a pretty clean signal for those. In some cases, clearly, one prefix versus another prefix may have completely different bandwidths. Sorry, one address within a prefix versus another one. My desktop, for example, has 100 megabits on it, and there are other prefixes, other addresses within the University of Washington that don't have anything close to that. So that's not going to tell you in all cases what the bandwidth is. But one of the ideas here is that then you can use a measurement of one prefix to be able to predict measurements of other prefixes. And it's not perfect, but it would be better than nothing. Okay, so we've measured links at the edge. We've measured properties of links in the core. We can predict routes. Therefore, we can compose properties of links in the core to be able to produce these end-to-end behavior. And then the question is whether the combination of these work. We have measured this as a kind of an example of how accurate these are for paths between Planet Lab nodes where we actually know what the data is, because we can control both sides. There is clearly room for improvement. If you look at cases where we actually have the correct AS path, that is, we're predicting it correctly, then we actually do pretty well. The red line is for all paths, and then where we don't actually know the AS path, we sometimes actually still get pretty close, but it's certainly, in terms of absolute error, much worse off. So one of the challenges that we have is how do we improve our AS path prediction, and that's certainly future work.
What was the difference between those two graphs, the one on the left and the right?
Oh, sorry. This is loss rate, and this is latency. So we're actually a lot closer with respect to loss rate, but you don't see very many losses anyway, so that's part of the reason for why it's true. Yeah?
This is Planet Lab, right?
This is Planet Lab to Planet Lab, right? Yeah. This is only for the, yeah.
Where are the nodes?
I believe it's measuring path. It's because we want to have known paths, and we're comparing the known paths. We're taking Planet Lab to Planet Lab measurements, throwing out those endpoints from our data set, building the predictions using all the other Planet Lab nodes and all the other information we would have in our system, and then using the prediction from there.
If the nodes are mostly in the US or mostly...
Oh, well, where are the nodes in Planet Lab? They are everywhere. I could pull up that, but essentially there's about 350 sites around the world. Covers 5 continents. Largely the U.S., largely universities in the U.S., but increasing numbers in Asia and elsewhere. A lot in Europe. So it has some distribution. It's not representative. You shouldn't think of it as being representative. You shouldn't necessarily think that these are representative data. It's more what this is really my goal is to say. Look, if we can predict the AS path, we actually do pretty well. And better than the black box techniques, even for latency. And recall that the black box techniques like Vivaldi and GNP don't have any indication of what loss rates would be. So it's actually, in that sense, a step forward. It actually doesn't cost very much to measure. And now the question is, how well does this do for improving performance? Here is a BitTorrent swarm using this information. So if the tracker returns, 2 cases you could have. The tracker returns random people. The tracker returns, this is the case where it's using Vivaldi, so it returns people who are close based on purely just on latency. So I would like to give people who are nearby each other, I'll return more of those than others. And to be clear, and then can I return the peers based on the predicted TCP throughput, that is a combination of latency and bandwidth for my transfer time. And the red line is that, which is to say that the swarm actually completes faster and you get better response time as a consequence of this. This is between Planet Lab nodes, so it's a little bit of a constructed case, but it's an example of something that you might be able to do. And then I have a couple other examples, but I'll probably skip by them. They're in the paper. Here's a kind of one example. If you look at a kind of another case study for it, if you look at the problem of Skype, one of the challenges Skype has is it's having to predict for setting up a phone call between any 2 points, predict for that phone call which intermediary point it's going to go through. Now Skype almost always goes through an intermediary point just because of the consequences of NATs. On both ends, often you'll have to connect to somebody else in order to be able to get through your firewall or your free NAT. As a consequence, it has to pick that intermediary point well, as if it picks one with a high loss rate on either end, it's not going to work very well. If it picks one with high latency, it's not going to work as well. So the question we had was kind of in terms of just in terms of trying to improve loss rate, could we find one that would work better than the ones that you would pick randomly or the ones that you would pick close to the source or close to the destination? And that's what that's supposed to do. Anyway, so these traces that we have for iPlane are all available on our website, and happy to talk to people about it afterwards. And then finally, I just wanted to talk a little bit about global reachability. And this really gets at one of the kind of most interesting things. One of my students went and got this, this quote out of Clark's paper. I apologize for spelling Dave's name wrong there. I didn't proofread it, I guess. Which is that the design of the internet was really targeted for the following thing, which is that the only failure that you observe is one where there's a partition, which is if there is connectivity, you should be able to get through. On the other hand, what you actually see on Nanog, one of the most so Nanog is this operator email list that tells you what actually is happening on the internet. And one of the most popular queries on that is can you reach me? So people basically continuously, they don't know whether the rest of the internet can reach them, and they don't know what to do about it. They have really no way of knowing whether it's happening, what you can do. So please go ping me so that I can know what's going on. So the question is kind of how often is this global reachability violated? That is, how often are there these black holes or reachability problems in the internet? And can we use these vantage points to be able, multiple vantage points and multiple information sources to be able to do it? And this is simply one where we take the data that we collected for iPlane and then use it and basically just process it, analyze it, for how often it's the case that these pings that we're doing to the prefixes are in fact having problems. And now we're going to state that there's a problem where I can't get to the destination and I can't get to the AS that's in front of the destination. So if I have both an AS problem and I can't reach the end destination, then I'm going to call that a black hole. And what was interesting about this is that in many cases, actually a really remarkable number of cases, you're seeing problems. And over a 4-month period, almost all prefixes had some kind of problem in them, which is, I think, pretty remarkable. And there are a bunch of questions that you could ask about this. And our system that we're currently building to do this is called Hubble, as you might imagine, for trying to understand black holes, which I think maybe we've done a better job of naming the system than we have in actually building it. But you can see, essentially questions that you might want to answer would be, how long do these things last? How many of them are happening? How persistent are they? And those kinds of things. So, for example, if we measure from, say, 30 Planet Lab nodes spread around the world to a particular prefix every 15, I think it's every 15 minutes, right? Every 15 minutes, how long do the outages that we observe last? How often do those things last? And the red line is that cumulative distribution of the, which is to say that you're seeing them, that they, most of them get resolved right away. Some of them last longer. Some of them last a very long time. So, hours. And then finally, one of the things that you might be able to do with this kind of data is, how often is it the case that that you're seeing kind of complete connectivity loss versus one where parts of the network are able to see through the black hole and other parts of the network are not able to see through it. So how often is it that that I've got a single homed AS that just simply goes offline and everybody behind it is dead for a while? Well, not much you can do about that case. But what's really remarkable here is that we were able to see lots of cases where multi-homed sites were losing connectivity for some large section of the network. Now, multi-homing is a technique which enterprises will very popular use for improving their internet connectivity. But if their ISP upstream from them doesn't announce when they have a problem, then their connectivity to half the network is not going to help them very much. So this kind of thing is actually something where you're seeing a really large number of these cases, were ones where the connectivity was in fact there, could have been established, but wasn't as a consequence of potentially routing policies or ISP behavior. And in many ways, you could think of this as kind of Byzantine behavior by the ISP, but one which potentially routing protocols could deal with, or overlays might be able to deal with. So the summary here is that internet measurement has a lot to offer distributed systems. We can build these systems that actually give useful predictions, that you can start to optimize distributed systems based on them, start to assume that every piece of information you might think of having it from the internet is stuff that is actually available and can be efficiently measured. We don't have to wait necessarily for the internet to be re-engineered for disclosing all this information. You don't have to wait for ISPs to suddenly wake up to think that it's in fact in their interest to tell us information about their underlying network. But rather, this is information you can find and then can actually optimize on. So that's where I'll stop and take questions if there are any. And otherwise, thanks very much.